Okay, so now, so we just did frequency encoding, which we argued was actually phase encoding. And so now we have to do phase encoding, which is the same thing. And so what we're going to talk about today is, how we do frequency encoding, which is one kind of phase encoding, and then phase encoding, which is another kind of phase encoding, and in order to actually generate a two-dimensional image. But before I do that, I just want to go back over the Fourier transform equation one more time, just in 1D, to really sort of pin down the relationship between the physical things, the actual sort of physical, gradients, and the Fourier transform. So the Fourier transform equation is, we have a signal, it's a complex signal, and that signal is a function of spatial frequency, so k is spatial frequency, and the Fourier transform says, how do you get one spatial frequency? You sum across x. So you sum across the x direction, and what are you summing? You're summing the value of the image at each point. So that's the brain. It's basically the proton density. So what is the proton density at that particular point in x? And then you're multiplying by the e to the minus I 2 pi, and then instead of f we have k, and then instead of time we have x. So when we first talked about, was f, and this guy, was t. So spatial, so k, we use k for spatial frequency, but it's the frequency variable. So what is so this is just the Fourier transform equation. So what is, what corresponds to what? And what is our actual data collection? So let's just draw out the gradient here. So here's, for instance, the gx gradient in time, and then here's our echo. So this is RF record, and here's our data. So here's our data samples that are being recorded. So what corresponds to what? So basically this signal that we're recording, is these are the individual spatial frequencies. So this would be like K1. Let's line this up with a little bit after the gradient goes on. So this would be K1, K2. Let me just, not K1, K2, let's just write it out as, this is spatial frequency equals 1, and this guy is spatial frequency equals 2, etc. So that's our data that's coming out of the phase-sensitive detection. So it's a complex number, an x and a y component, and then we're summing up across the image. So, what's doing the summing? Well, the summing is basically the RF coil. So the RF coil is not paying any attention to where it is. It's just adding up across the whole brain. And then, what is this? This is basically, the image, proton density. So that's the actual brain. And then where does this come from? So this is cosine of, you can sort of divide that complex number up into cosine 2 pi, the current spatial frequency, times the current x position, and then minus sine 2 pi kx. And what is that? Well, that's a vector of, length 1, and that's just basically the real and the imaginary part of that vector. So you can either write it out as one thing, or you can write it out as sines and cosines, and of this angle here. And the minus is because of that minus. So this minus here appears there. So, and what causes that? This is what the gradients do. So the gradients, so the spatial frequency that you get is basically just equal to the strength of the x gradient times time. And so why is that? Well, if you have the gradient on for some amount of time, you get a certain spatial frequency. If you leave it on for twice as long, t is twice as long, you get twice the spatial frequency. So basically just the amount of time that it's on is proportional to the spatial frequency that you get. So if you leave it on for 10 units, you get spatial frequency 10. You leave it on for 1 unit, you get spatial frequency 1. So there's a very concrete, specific relationship. This all corresponds to real stuff in the world. This is the actual signal where we record. The RF coil is doing the sum. What is it summing? It's summing the number of protons at each point in X, and it's multiplying by this complex vector. So this is a complex multiply. This guy is real, but this guy is complex. And what is this? These are the stripes. These are the spin stripes. So they move across X. As you move across X, you can either think of it as a vector rotating around as you go in the X direction. That would be this view up here, or you could think of it as a sine, a cosine and a sine as you move in the X direction. So that's the spatial frequency. So this is the spatial frequency, and but I like to call it just the spin stripes. So it's the spin phase stripes. Phase stripes. So that's spatial frequency that the gradients are causing, and this is caused by the gradients. So that's our very concrete relationship between the Fourier transform and the hardware. So what we're doing is the hardware is performing a physical Fourier transform, essentially. It's doing this integral. It's summing across all of X, taking whatever the brane is at each point in X and multiplying it by a sine and a cosine, or you can think of multiplying it by this, a unit length equals 1 vector pointing in some direction around the XY axis, and then summing that all up, complex sum. What does that mean? That just means vector sum. Tip to tail. So take each transverse magnetization vector, add them all up, and then you get the resultant. So it's a vector sum. Okay, so that was just trying to directly relate what we did last time to the equation, which we already went over the equation a bunch of times, but it doesn't hurt to go over it over and over. So that's the basic direct relation between the hardware performing a physical Fourier transform of the brane image. into this spatial frequency data. So this is spatial frequency data. So now what? So now the plan is, let's talk about phase encoding. So this is just 1D. So this was just one-dimensional Fourier transform. So obviously we need to be able to do this in 2D or 3D. And so now the problem is we have to sort of go up to the 2D or the 3D Fourier transform. But before we do that, let's just, for me, the most concrete way to think of this is to think about what's actually going on in the physical world. So what is going on in the brain slice? So we don't have any complex numbers, we just got something going on in the brain slice. So that's the way we want to look at it. So before we do that, we would just want to draw out what's happening with the gradients. So the main difference between the phase encoding and frequency encoding for a standard pulse sequence, the only difference really is when you turn the gradients on. And so here's our RF pulse, and the first thing we do is we select a slice. So we have to turn on, so this is a frequency selective RF pulse combined with a gradient is a way of just exciting the spins in a slice. And then here's a little fixer. And then what we do, actually, in MRI you always want to, you never want to waste any time. So it turns out as soon as you finish the RF pulse, you can go ahead and start your phase encoding. So here's our phase encoding. So we'll draw this out like that. And it's often drawn out with that little diagram like that. And what that diagram means is repeat this whole procedure, setting the gradient to all these different locations. So this is you can think of it as a loop. So it means like for each setting of the GY gradient, repeat the whole thing. And then what are we repeating? We're repeating the data collection. So here's our X gradient, and the first thing we do is we sort of go negative, and then we turn the gradient on positive and do our so-called readout. And that corresponds to the actual center of that corresponds to the center of the echo. So there's the echo right there, and there's an FID here which we're not paying attention to. And so this is our actual data samples here during the readout. So the labels are, so this guy is, slice select. This is so-called phase encode. This guy is, readout. Or frequency encode. So I'll put that. So this is called frequency encoding, although I told you it's actually just phase encoding, and then it's often also called the readout. So what we want to try to do is, so the only difference here is that, basically you've turned the phase encode gradient on earlier than, before you actually started any recording. Now, you shouldn't sort of fasten on to that, because it turns out you can turn the phase encode gradient on at the same time as the readout. And there's a kind of pulse sequence called a spiral pulse sequence where the phase encode and the readout are on at the same time. So that's not a critical It's not a critical distinguishing feature. The fundamental distinguishing feature is really only that it's in a different gradient. That's the only difference, really, fundamentally, conceptually, between phase encoding and frequency encoding, is that it's just a different gradient. The gradient is in a different direction in space. And so now we have to sort of figure out, well, how do these things interact with each other? So the problem is, how if we're putting the gradient on, it's going to affect all the spins. And if we put the X gradient on, it's also going to affect all the spins. So how do these things interact without messing each other up? So that's the goal for today. And so so the picture we have, and I'll fix the shading in my notes. I noticed I had the shading in one of the diagrams was reversed, but I'll fix it and post new notes tonight just to sort of fix the shading. I'll fix it in the diagram here, so it'll be slightly different than what you see in the notes, but this is correct. So what we want to do is we want to look down. Let me just draw this a little bit lower. So we want to look down on a slice. So when I'm drawing, so the picture I'm drawing here is looking down on slice. So look at a slice from the sort of the perpendicular to the slice. And then we'll consider the effect of phase encoding, and then the effect of frequency encoding, to try to see how they interact with each other. So let's assume that the X, this is the X direction, and the Y direction, that's the actual real X and Y in space. So this is the frequency encoding direction. And so we haven't turned the frequency encoding on. So at this point in time, frequency encode Kx equals 0. So the spatial frequency in the X direction is 0. And now let's assume that we've picked out one of these gradient levels that corresponds to phase encode spatial frequency Ky equals 4. Okay, so that might be, the middle one, because the top one it could be something like phase encode spatial frequency equals 128. But say it's hard to draw 128, so we'll draw 4. So basically there's going to be 4 stripes of phase across the slice going in the Y direction. And so what direction here's where my coloring was incorrect, and I'm coloring in dark. My coloring signifies dark, which means small, and light, which is no coloring, signifies more positive. And what I'm coloring here is basically the spin phase. So I'm coloring. I could do it with arrows, but then it really gets really horrible. So what does this correspond to? This corresponds to, I'll just draw one set of arrows so you get the idea. So this is supposed to be spin phase 0 going that way. And now we're going to be increasing. So our angle is increasing. And by this time we're already that way. So and then we are down this way and then down this way. So that's basically our, so to the right, and then we rotate downward. Oh, did I do it backwards? How many flips can Marty do? Okay, so we start off at 0, and then we're going positive. Maybe I did it right. Okay. And now we're going that way. Now we're back that way. Okay. So basically what's happening is you're going, as you go through, you're going through like that direction. Or you could sort of think of it as we go this direction, we're going in a negative direction, because that's the that's the negative I, 2 pi kx. It's that negative there. So if you start at the bottom of the slice, we're going negative angles around. So if I did it really big, so we start this way, and then as we move up the slice, we rotate around like this until we end up back at 0 degrees. And I'm trying to indicate that picture with the coloring. So here we're at 0 degrees, and here we're at, slightly more than 0 degrees, and so on. Okay, so we've got four stripes of spin phase across the brane, because we did whatever the gradient strength required to get these guys four behind, really. So so if we draw out, we could draw out on this side, we could draw out the phase. So if I draw out the phase, which way did I have up? I have up going this way. So if this is 0 and 2 pi that way, then the picture of phase, that should be 0 going up to 2 pi and then back down to 0, because it's a circular variable and it wraps like that. Okay, so we got four cycles of phase going across the brane in the y direction, because we turn this one of these gradients on in the y direction. Okay, so that's the state of phase encode spatial frequency in the y direction equals 4 before we've turned on the readout. So this is before readout. And for the time being, I'm going to ignore this negative part here. We'll come back to that, but we'll just ignore this negative guy for the time being, just to make our diagram a little simple. I'll draw it out below here what actually is happening. Okay, so that's phase encode spatial frequency 4. So now the problem is we have to do the readout. And so when we do the readout, we're still going to have, so we turn on, we basically turn on the x gradient during the readout. But if you remember, the x gradient changes bz in the x direction. The y gradient changes bz, same thing, in the y direction. So they both affect the same thing. So the first question that comes to mind is, how come they don't mess each other up? Because when you turn a gradient on, it changes the bz, which is the thing that causes the spins to get ahead, because it's changing the frequency of the Larmor frequency of the oscillation, of the precession oscillation. How come they don't all mess each other up? And the answer is they actually do. So when you turn the y gradient on, it affects all the spins in the brane. When you turn the x gradient on, it also affects all the spins in the brane. So how can they sort of somehow not interact with each other, even though they actually are interacting with each other? And so what we're going to draw out is frequency encode kx equals 10. So this is during readout. So this is just a snapshot of in the middle of the readout. So that would be, say like here. Well, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there's 10. K x equals 10. So how could they possibly not interact with each other? So so the plan is, let's see if I can do this approximately right. So what we want is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 stripes in that direction. So 10 stripes in that direction. So let's see. Let's try an angle like this. See how that works out for us. Did I get? Yeah. Okay, that's pretty good. Okay, so now what we've got are these tilted stripes. So the coloring on the stripes, here's the lowest angle, and then this is kind of so we've kind of rotated the stripes like this, etc. I won't draw the rest of them in. So if we draw the phase going in this direction, what does it look like? Well, it looks like it starts at 0, and then it goes up, and then it goes down, up, down, up, down, up, down. I didn't get 10, did I? I got 10 up there, but I straightened out my stripes a little bit over here. I didn't move them over enough. Okay, get them a little closer this way. There we Okay, something like that. So there should be 10 here, etc., going that direction. Now, if we go in this direction, we haven't done anything to the phasing code, and so the phasing code should just be the same as it was. So this is 0, 2 pi. This is 0, 2 pi. So the question is, how can we how does this work so that it doesn't mess up the other direction of stripes? And the answer is, if we actually just count, if we go in this direction, so basically if we start here and say, how many wraps in spin are there? Then we would say there's like 1 wrap in 2 wraps, 3 wraps, 4 wraps. Slightly tilted, but pretty close. So if we move across this tilted stripe pattern, we only run into 4 stripes. So that's the same as what we had before. If, on the other hand, we go across the situation here, we should end up with 10. Let's see, so 1, 2, 3, 4, 5, 8, 9, 10. Okay, 10. So there's 10 stripes. Whenever you go across in the x direction, there's 10 stripes. Whenever you go across in the y direction, there's only 4. Now, how could that happen? Because you've actually messed with all the phases of all the spins. The x gradient has touched all the spins, and the y gradient has touched all the spins. And so if you look at a particular point in here, so let's just pick out, say, a particular point in the brain. there. So what does that correspond to back here? That corresponds to this point. So if you look at that point, what is the status after we did the phase encode? So this guy was 2 ahead. So now what's the situation here? So what's the situation here? It's 2 ahead. It's 2 ahead from this, but then it's got an additional 1, 2, 3 ahead. So it's 2 ahead plus 3 ahead, equals 5 ahead. So it's actually, so this guy, after you did the frequency encode, this guy's actually 5 cycles ahead. Whereas after you did the phase encode, it was only 2 ahead. And yet, even in spite of that, if you go across the brain in the y direction, you only run through 4 cycles, the same 4 cycles you had here. And if you go across the brain in the x direction, even though some of these guys might be 3 ahead over here, you still only run into 10 stripes. So the 4 doesn't add to the 10, and the 10 doesn't add to the 4. So that's basically how you can sort of see that from this diagram. You can clearly see that we're doing exactly the same thing in phase encoding and frequency encoding. We're just stamping on stripes, and the only difference is what direction we're doing it. And the reason that we can get away with doing 2 phase encode directions, basically, is just strictly because they're perpendicular to each other. So as long as the gradients are perpendicular to each other, if we go back to this picture and move in the x direction, we don't see any spin stripes here. These guys are all 3 ahead, and so but if we move in the x direction, it looks like there's no wrap in phase. And now if we move in the x direction, there'll be 10 wraps in phase. But we kind of ignore the 3 because we can't see it, because it doesn't change when we move in the x direction. But exactly the same thing applies here. So when we move in the y direction, when we move in the x direction, we can't see these guys. When we move in the y direction, we can't see these stripes that were put on by the frequency encoding. So what's going on? You're just adding the angles, but because the angles wrap around, it's the property of a complex variable, a circular variable. When we're adding these angles in a circular variable, they just wrap around and sort of get back to where they were before. And so you actually can't see, when you're moving in the x direction here, you can't see the fact that these guys are all 3 ahead, because the angle wrapped around again to the same way as it would have been if you hadn't turned the gradient on at all. So that's the main point of how you can make images. And you could easily imagine how you could extend this out into 3D. And I'll talk about that in a little bit. But this is an important thing. If you can sort of get this idea of you're just warping, you're wrapping up the spins, and the only difference between the phase encode and frequency encode is just the direction that you're wrapping the spins up in. And the way that they manage to not interact with each other is just because of having a circular variable, and when you apply these gradients in perpendicular directions, you essentially can't see the wraps in the other direction. But physically, what actually happened was the guys here are 5 ahead, but here they're 2 ahead. But you didn't mess up. They didn't interact with each other. So that's frequency and phase encoding. So how does it work in real life? So I drew it out here without this business here. So let's consider what's actually happening when you do that. So when you do that, so let's look at what does the actual echo look like? Why do we draw it like that? So basically, what's going on is if I draw that echo out, So here's the echo, drawn out. So it's a slow thing like that, and looks something like that. So what does that correspond to? So this is time during the readout. And so what happens? So we didn't do any recording before until this little negative gradient ended. So what does the negative gradient do? Well, the negative gradient is going to, instead of tilt the spin phase stripes up this way, it's going to tilt them the other way. And so you can think of that, if we look at the first recording point, we're going to have like 128 stripes tilted off to the left like that. That would be like right here. So here, this point, corresponds to here. And then what'll happen is now we've got the gradient on reversed, and so it'll be unwrapping the stripes instead of wrapping them. And so then what's going to happen is, the stripes will start to unwrap and notice they'll actually sort of get spaced further apart. And, eventually they'll, get more unwrapped. And when you get to the middle, what happens? So when you get to the middle, there's no stripes. So there's no stripes at the middle, also known as the echo. So that's the echo. No stripes. And what does no stripes mean? No stripes is the special center of k-space. It means kx equals ky equals 0. They both equal 0. So right at the middle, so this guy is, this guy goes there, and this guy is somewhere here. So right at the middle, there's actually no stripes. And then you just continue sort of wrapping them up the other way, which is what I drew here. So now they're sort of, going the other way like this. So here they're not that far. Here they're kind of getting closer to each other. And, eventually we get all the way up to 128 going the other way. So that's what actually happens. So the first thing we do here is we wrap everybody up as far as we can in this direction at the same time as we're doing the phase encode. So we're sort of adding stripes in this direction. And then we unwrap these guys and then wrap them up the other way. And when we hit the middle, there's no stripes. So the spins should all be lined back up again. Of course, they're not going to be completely lined back up again because, there was T2 star decay. We can't fix that because we're doing a gradient echo. But for all practical purposes, they get all lined up again, and that's the biggest signal. That's why it's the echo. It's the echo because there's no stripes, because stripes are bad for the signal. Stripes kind of like distribute the spins in different directions, and so they're generally going to be less signal. These guys are much smaller signals, so when there's no stripes and they're all pointed in the same direction, that they'll vector add up the biggest, and that's why that's the echo. So we finally sort of brought together the echo with the Fourier thing. So the echo is kind of a whole sequence of different spatial frequencies, different combinations of spatial frequencies. And there's no stripes only if we happen to be, edit that. There's no stripes only if we happen to be at the 0 phase encode. But the example I gave here was the 4 phase encode. So the answer would be 4 stripes here. So let's just, so the idea is that if we a valid phase encode is the phase encode gradient off. During the phase encode gradient off, when we go through the center of the readout, we'll have no stripes. So this is, let's edit my diagram here. So you know, now we just have KY stripes. And then a special case. Special case, which is KY equals 0, is no stripes. So in this case that I drew here, where we did phase encode 4, we put on 4 stripes in the y direction, and then we added to that using this kind of method, except reversed. Instead of going this way, we went the other way. We added 128 stripes, and then we unwrapped those 128 until we got back to 4 in the y direction, and then we wrapped the other way until we got up to 128 in that direction. So that was what that described, was one line of data for. So this was one line of data for KY equals 4 and KX equals minus 128 to plus 128. So that would be 256 data points. They all had spatial frequency y equals 4, and then they had all these different spatial frequencies for x. Yeah, and then in the special case, when phase encode happened to be 0, then we would have no stripes, and that would be the center of k-space. So no stripes in the y direction, no stripes in the x direction. Because this state of ky number of stripes, 4 stripes, turns out to be 0 stripes in the x direction. That's 0 stripes in the x direction, like this state right here. You go in the x direction, you don't get any change in phase. Okay, so how does that work out? The last thing in the last 2 minutes, how does that work out with the Fourier transform equation? And it turns out it's very straightforward. All we have to do is add another angle in there, and that's just exactly what we're doing here. We're just adding an angle. We're adding an angle, and it just happens that if we add an angle as a function of x position, it won't mess with our angle in the y position. Or if we add an angle in the y position here, it won't change our angle when we move in the x direction. And so the 2D Fourier transform equation is actually very simple. It just has for a single complex value that's defined for 2 spatial frequencies, the x and the y spatial frequency, the equation is just simply to add up the angles in the x and the y direction. And so now we have to do a double integral. That just means for each x, and then for each y, go to each x. So that means in other words, for all combinations of x and y. We now look at the image at an xy point. So that's a two-dimensional. We have a two-dimensional image, and that just means just get some xy point in the image, and then multiply it by this same e to the minus I 2 pi. But the only difference is we're adding the angles here. And so it's kx times x, and then we're adding the ky times y. Now we could write that out. You could also write that out when you add exponents. It's equivalent to multiplying the whole thing. So that equals, e to the minus I 2 pi kxx times e to the minus I 2 pi ky times big Y. So, and we already know that from complex multiplication. When you do complex multiplication, that's equivalent to adding the angles that are in the exponent. But we can also just write that out like this, just add the angles directly in the exponent, and that sort of corresponds intuitively to what's going on here. We add the stripes here, we're just sort of we're adding some angles to everything, the whole brain. But because it's in a different geometric direction, it doesn't interact. And so and then summed across, these are, for each little x and y increment. So once again, this is our RF coil signal. That's complex. The RF coil does this. Does complex add. It's a complex number. It's doing a vector sum. That's the signal equation. That's the fact that we've got phase-sensitive detection, and so we're actually able to get a two-dimensional signal, and so that we can sort of do a vector sum. This is our slice. Proton density at each point in the slice. At each xy point. And then these things are the 2D stripes. 2D stripes. And there's all different possible combinations, and so you can think of it as either, all combinations of x and y stripes. So all combos of kx and ky stripes. But since the way they interact is by rotating the stripes, you can sort of think of it it's kind of easier to think of it in polar coordinates, which is basically all combos of orientation and spacing. That's the way I like to think of it, and stripe spacing. So all combinations of stripe orientation and stripe spacing. And stripe spacing. So, and that's, you can sort of see that, you can see that down here. So basically what you need to do is, you need to collect data for every possible combination of orientation of the stripes, but then at each orientation you've got to collect all the different possible spacings of the stripes, from like zero stripes up to 128 stripes. So then it's if you can get through this, well, then it's easier to imagine how you could do a 3D sequence. So a 3D, a 2D sequence looks like, let's just pick out a slice like this and then put stripes on it. So that's 2D. So what is 3D? Well, 3D is, let's just excite the whole brain. Just excite the whole brain and then put stripes on the whole thing. So, you'll end up with some arbitrary set of stripes across the whole brain like this. So that's 3D. And how do you do that? Just turn on the Z. turn on the Z gradient at the same time. So you got all three gradients on at the same time. And then what do you have to do? You have to collect all the different orientations of stripes, but now they can rotate in 3D, so you have to consider all the different possible orientations of stripes, and then at each orientation, all the different spacings of the stripes. And that's a lot. That might be, say, like 10 million. So you got to collect 10 million data points. But you're doing it really quickly. And so that's, this is an example of like something like an MP range, a typical structural scan. You're going to have 10 million data points. And what does that correspond to? 10 million combinations of stripe orientation and stripe spacing. So it quickly sort of, ramps up. But the key understanding is that just by putting on the gradients in different directions and having a circular variable, you can sort of set up a situation where they don't interact with each other, even though they are interacting with each other. Every gradient touches every spin. But magically, we can sort of consider them to sort of be completely non-interacting. So we can just turn on different gradients at the same time and just act as if they weren't interacting, even though they are. Okay. So I think we're ready to end the recording, David.